Black holes are enigmatic cosmic phenomena that captivate scientists and enthusiasts alike. These regions of spacetime possess gravitational forces so immense that even light cannot escape, rendering them invisible to the human eye. Their formation begins with the death of a massive star, where the core collapses under its own gravity, leading to the creation of a singularity, a point of infinite density surrounded by the event horizon, the boundary beyond which nothing can return. The journey of a black hole begins in the heart of a dying star, where nuclear fusion no longer provides the energy to counteract gravitational collapse. When the core collapses, it creates a gravitational well so deep that spacetime around it becomes warped. This warping of spacetime causes strange phenomena, such as time dilation, where time slows down significantly near the event horizon compared to distant observers. The deeper you go into a black hole's gravitational pull, the more distorted reality becomes. Black holes are not uniform, they come in various sizes and categories. Stellar black holes are a few times the mass of the Sun, while supermassive black holes at the centers of galaxies can be billions of solar masses. Intermediate black holes, which are less understood, occupy a space between these extremes. There is also the possibility of primordial black holes, hypothesized to have formed shortly after the Big Bang, though their existence remains theoretical. Observing black holes directly is impossible, but their presence is inferred through their interactions with surrounding matter. When matter spirals into a black hole, it forms an accretion disk, heating up due to friction and emitting powerful X-rays detectable by telescopes. These emissions provide a glimpse into the immense forces at play and the chaotic environments surrounding black holes. In 2019, the Event Horizon Telescope project achieved a monumental breakthrough by capturing the first image of a black hole, marking a significant milestone in astrophysics. The singularity at a black hole's core is a region where the known laws of physics break down. General relativity describes the warping of spacetime caused by a black hole, but it cannot explain what happens at the singularity itself. Scientists are striving to reconcile general relativity with quantum mechanics to gain a deeper understanding of these mysterious points of infinite density. What lies beyond the event horizon remains one of the greatest mysteries in modern science. Black holes play an essential role in shaping the universe. They are not merely destructive forces but also cosmic architects, influencing the formation and evolution of galaxies. The supermassive black holes at galactic centers anchor these vast systems, providing the gravitational stability needed for stars to orbit. Their immense energy output, especially during periods of high activity, can regulate star formation by expelling gas and dust. The concept of black holes challenges human understanding of reality and stretches the limits of imagination. They represent a unique intersection of astrophysics, cosmology, and philosophy, forcing us to question the nature of space, time, and existence. Some theories even suggest that black holes could be portals to other dimensions or alternate universes, though such ideas remain speculative and unproven. While black holes might seem like cosmic destroyers, they are not an imminent threat to Earth. None are close enough to pose any danger, and their effects are felt only within a limited range. However, their study continues to unveil profound insights into the mechanics of the universe and the fundamental forces that govern it. With advancements in technology, such as gravitational wave detectors like LIGO, humanity is beginning to uncover the secrets of these extraordinary phenomena. The study of black holes is still in its infancy, and each discovery opens the door to more questions. These entities push the boundaries of our understanding, revealing the intricate dance of matter, energy, and gravity in the universe. As we delve deeper into their mysteries, black holes promise to remain a source of endless curiosity and inspiration for generations to come. A black hole emerges as the ultimate end stage of a massive star's life cycle. When a star exhausts its nuclear fuel, it loses the outward pressure needed to counteract its own immense gravitational pull. This imbalance causes the core to collapse under its gravity, forming a singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon, an invisible boundary that acts as the threshold beyond which escape is impossible. The event horizon defines the point of no return. Once any matter or energy crosses this boundary, it is inexorably drawn toward the singularity. The escape velocity required to break free from a black hole's gravity exceeds the speed of light, rendering it impossible for anything, even light, to escape. This makes black holes invisible, detectable only through their effects on nearby matter and light. The gravitational pull of a black hole warps spacetime to an extreme degree. This warping creates fascinating phenomena such as gravitational time dilation, where time appears to slow down for an observer near the event horizon compared to someone far away. If you were to watch an object falling into a black hole, it would seem to freeze at the event horizon, its light redshifting until it fades from view, a result of this distortion of spacetime. Black holes come in different sizes, dictated by the mass of the star that forms them. Stellar black holes, born from individual stars, typically have a few times the mass of our Sun. In contrast, supermassive black holes, found at the centers of galaxies, can contain millions or billions of solar masses. Despite their immense gravitational influence, their event horizons span vast distances, making them surprisingly diffuse in terms of density when scaled to their size. The singularity at the heart of a black hole represents a mystery that continues to baffle scientists. At this point, gravity becomes infinitely strong, and spacetime curves infinitely. General relativity predicts the existence of singularities, but it cannot describe their nature. Quantum mechanics, which governs the behavior of particles at the smallest scales, has yet to provide a clear explanation, leading to ongoing efforts to reconcile these two foundational theories of physics. Black holes are not merely destructive entities. They play a vital role in shaping the universe. Supermassive black holes, for instance, influence the formation and behavior of galaxies. Their immense gravitational pull holds galaxies together, while their energy output during active phases can regulate star formation. By consuming matter and releasing intense radiation, black holes contribute to the dynamic processes that shape the cosmos. While the interior of a black hole remains inaccessible to observation, its presence can be inferred from its effects on surrounding objects. Gas and dust spiraling into a black hole form an accretion disk, heating up as friction generates X-rays and other forms of electromagnetic radiation. These emissions, detectable by telescopes, provide valuable insights into the environment around black holes and the processes that govern their behavior.
The concept of the event horizon introduces intriguing philosophical and scientific questions. Anything crossing this boundary is effectively removed from the observable universe, taking with it all the information about its previous state. This has led to debates about the information paradox in physics, as it challenges the principle that information cannot be destroyed. Resolving this paradox remains a significant focus of theoretical research. Despite their reputation as cosmic monsters, black holes are not inherently dangerous to the universe at large. Their effects are confined to their immediate vicinity, and none are close enough to threaten Earth. However, their extreme properties make them excellent laboratories for studying the most fundamental aspects of physics, including gravity, quantum mechanics, and the nature of space-time itself. The study of black holes is a journey into the unknown, challenging our understanding of the universe at every turn. They are a reminder of the vast and mysterious cosmos that lies beyond our everyday experience. By exploring black holes, we deepen our grasp of the laws governing reality and unlock the secrets of existence on the grandest scales imaginable. Black holes come in various types, each with unique characteristics and origins. Stellar black holes form when massive stars run out of nuclear fuel and undergo gravitational collapse. These black holes typically have masses a few times that of our Sun and are relatively small in size, yet their gravitational influence is immense. They often arise in binary star systems where their presence is revealed through interactions with their companion stars, such as by accreting matter and emitting X-rays. Supermassive black holes, in contrast, are colossal entities found at the centers of galaxies, including our Milky Way. Their masses range from millions to billions of solar masses, dwarfing stellar black holes in scale and influence. These giants are thought to form through the merger of smaller black holes and the accretion of vast amounts of matter over time. Their gravitational pull governs the dynamics of entire galaxies, anchoring stars and gas clouds in their orbits. Intermediate black holes occupy a middle ground between stellar and supermassive black holes. These elusive objects are challenging to study due to their rarity and limited observational evidence. They are believed to form in dense star clusters, where repeated collisions and mergers of stars and smaller black holes create objects with hundreds to thousands of solar masses. Intermediate black holes may represent an evolutionary step toward the formation of supermassive black holes. Primordial black holes are a theoretical class of black holes that could have formed shortly after the Big Bang. Unlike other types, they would not originate from stellar collapse, but from high-density fluctuations in the early universe. If they exist, primordial black holes could range in size from microscopic to planetary-scale masses. They are an intriguing candidate for dark matter, potentially explaining some of the universe's unseen mass. Each type of black hole exhibits distinct behaviors and interactions with its environment. Stellar black holes can emit bursts of X-rays when accreting matter, while supermassive black holes can generate quasars, some of the brightest objects in the universe. These quasars result from immense energy released as matter spirals into the black hole's accretion disk, illuminating vast distances and revealing the presence of the black hole itself. Intermediate black holes may help scientists understand how supermassive black holes grow and evolve. Observations of star clusters and gravitational waves from black hole mergers are providing new clues about their formation. Similarly, the search for primordial black holes involves studying their potential effects on the universe, such as their influence on the cosmic microwave background or their role in gravitational wave detections. The study of these different black hole types sheds light on the diversity and complexity of the universe. Stellar and intermediate black holes are crucial for understanding the life cycles of stars and the dynamics of star clusters, while supermassive black holes reveal the processes shaping galaxies. Primordial black holes, if confirmed, could provide insights into the conditions of the early universe and the nature of dark matter. The behavior of black holes also varies based on their size and type. Stellar black holes primarily interact with nearby stars or gas clouds, while supermassive black holes can influence entire galaxies. The differences in scale and interaction offer valuable perspectives on gravitational phenomena and the role of black holes in cosmic evolution. Each type of black hole adds a piece to the puzzle of the universe's structure and history. By studying these mysterious objects, scientists hope to answer fundamental questions about the formation of galaxies, the evolution of stars, and the origins of the universe itself. Black holes, regardless of type, remain a testament to the immense power and complexity of the cosmos. Black holes are extraordinary entities that warp the very fabric of space-time, an idea explained by Albert Einstein's theory of general relativity. This warping occurs because massive objects, like black holes, create a gravitational well in space-time. The closer an object is to the black hole, the stronger the gravitational pull, and the more extreme the distortion of space-time becomes. This phenomenon affects both the flow of time and the path of light. Time dilation is one of the most fascinating effects of a black hole's gravitational pull. As an object approaches the event horizon, time slows down relative to an observer far from the black hole. To an external observer, the object appears to move more and more slowly as it nears the event horizon. This is because the intense gravity stretches space-time to such a degree that time itself is altered, a concept that defies everyday experience. Light is not immune to the effects of a black hole's gravity. As light waves attempt to escape the gravitational pull near the event horizon, they lose energy, causing their wavelengths to stretch and shift toward the red end of the spectrum. This phenomenon, known as gravitational redshift, makes light appear dimmer and redder to distant observers. If the light comes from within the event horizon, it cannot escape at all, rendering the region completely dark. The warping of spacetime by a black hole creates unique observational effects. For instance, if you were to observe an object falling into a black hole, it would seem to slow down and freeze at the event horizon. This apparent freezing happens because the light emitted by the object takes longer and longer to reach the observer. Eventually, the object fades from view entirely as its light becomes infinitely redshifted. These effects have been observed and studied using advanced technology, such as the Event Horizon Telescope, which captured the first image of a black hole's shadow. The image revealed the silhouette of the event horizon surrounded by glowing plasma. This observation confirmed the warping of space-time predicted by general relativity and provided direct evidence of a black hole's influence on its surroundings. The extreme warping of space-time near a black hole leads to theoretical phenomena, such as the possibility of wormholes. Some theories suggest that the intense gravitational forces could connect different regions of spacetime, potentially creating shortcuts between distant parts of the universe. However, these ideas remain speculative and unproven, as no direct evidence of wormholes has been found. Inside the event horizon, spacetime curvature becomes so extreme that all paths lead toward the singularity. At this point, the concepts of space and time as we understand them cease to exist. The singularity represents a boundary where current physical theories break down, and scientists are working to develop a quantum theory of gravity to understand these regions better. The effects of black holes on spacetime extend beyond their immediate vicinity. Their immense gravitational pull influences the orbits of nearby stars and the motion of galaxies. These interactions provide indirect evidence of their presence and allow scientists to study their properties without directly observing the black holes themselves. Black holes challenge our understanding of reality by revealing the malleability of spacetime under extreme conditions. They demonstrate that time is not a fixed constant, but can be stretched and altered by gravity. These insights have profound implications for our understanding of the universe and the fundamental nature of existence. The warping of spacetime by black holes serves as a reminder of the universe's complexity and the limits of human understanding. By studying these phenomena, scientists hope to uncover deeper truths about the cosmos, bridging the gap between general relativity and quantum mechanics. Black holes continue to captivate and inspire, offering a glimpse into the intricate fabric of reality itself.